last day we have seen this. This is the definition for an open set. Okay. So the first example that we had done was every open interval is an open set. Okay. Open interval is an open set. Open set. So let us do this again. So how will you solve this? Let A comma B subset of R be an open interval. Be an open interval. Open interval. So I have to show that for each x inside this interval, I can find a open interval of this type. Okay, whose center is x. So let small x belongs to AB be any element. Okay, be any element. Okay. Then if you remember the diagram that I had done last day, so x may be a point here. X side will be what? So in that case, if you draw a open interval of this length, x minus a, this length, okay, then this x minus epsilon to x plus epsilon, this will be a subset of AB. No? But if you draw an open interval of this length, b minus x, then what will happen? This side is okay, but this side it will come outside the original side. Actually, epsilon is this distance. Okay. If I take epsilon as this distance, then x minus epsilon to x plus epsilon. This is a interval inside AB. Okay. But if I take epsilon as this distance, then what happens? X plus epsilon will be somewhere here, and x minus epsilon will go outside the set. Okay. So that means we have to choose the epsilon as the what? Minimum of these two distances. Okay. X minus a, b minus x. If x is somewhere here, then which distance we should take? We should take this b minus x. Okay. So whichever is smaller, we will take that distance as epsilon. Okay. So we can take epsilon as minimum of x minus a and b minus x. Okay. So that way we will construct one open interval, which will lie inside this AP. Okay. So in last class I had taken half of that. So half is also not required. So that's why I am doing it again here. You do it this way. So we take epsilon equal to minimum of this distance, x minus a and b minus x. Right. So why I have taken x minus a? Because x is greater than a. X is a point inside AB. Okay. So x is greater than a but less than a. So x minus a is positive and b minus x is positive. So that is why we take epsilon as minimum of x minus a comma b minus x. Okay. Then this interval x minus epsilon to x plus epsilon. Okay, this is an interval which is a subset of AB. Okay. So how this is a subset we'll just justify. Okay. How this one is a subset. So to justify this, let y belongs to, I have to show this set is a subset of this set. That means every element of this set is an element of this set. No? So I start with an arbitrary element of this set. A set of arbitrary element ki shuru karo. I will start with y belongs to this, then I will show that y actually belongs to this. Okay? This is what we do. So let y belongs to x minus epsilon to x plus epsilon. Okay? Then, so what does this imply? This implies that, the next line you can write, this implies x minus epsilon, y lies between these two values. X minus epsilon to x plus epsilon. Okay, y lies between these two values. Okay, that is the definition of interval. Okay. So, so from there, what can you write? From there, I can write if I take x to the other side, so it's minus epsilon less than y minus x less than epsilon. Okay. Right. Now, y minus x is less than epsilon, and again epsilon is less than or equal to what? what is epsilon? Epsilon is minimum of x minus a comma b minus x. Okay. So this is always less than or equal to what? This is less than or equal to. This is the minimum of these two. So it is less than or equal to each of these two values. Say minimum of 2 comma 3. This is, I can always write this is less than or equal to 2. It is also less than or equal to 3. It should be less than both. Okay, minimum of this two is less than 2. Right? That is the thing. So this is, I can write this is less than or equal to. So I will write this is less than or equal to, say this one, b minus x. Okay, this is less than or equal to b minus x. So therefore y minus x is strictly less than. So ultimately I have y minus x is strictly less than b minus x. Okay. Now you take x to the other side. So this will mean that y is strictly less than. This x will get cancelled. So y is strictly less than b. So this implies y is strictly less than b. Okay. Also, we will show that y is strictly greater than a. Okay. This is what we will show. So we will show it from this part. Okay. A part. Again, minus epsilon is less than y minus x. Okay, so this means that if you multiply both sides by minus 1, so its epsilon is greater than x minus y. Okay, epsilon is greater than x minus y. Right? So from there we will get epsilon is greater than x minus y. Okay, so that is x minus y is strictly less than epsilon. But this is again less than or equal to a minus x. X minus x. Okay. X minus. So from here, what do I have? X minus y is strictly less than x minus a. So x gets cancelled. So minus y is strictly less than minus a. That is y is greater than. Okay. So this is, so you can take 1. This is. So what I have proved? I have proved that y lies between, from 1 and 2 we can write, from 1 and 2 we write a less than y less than, okay. So that is y belongs to open interval. Okay. So if y is an element here, y is also an element here. Okay. So this is what we are doing. Okay, this is less than or equal to this because epsilon is what? Epsilon is minimum of x minus a comma b minus a. So it is less than both of them. Less than or equal to both of them. So that's what we have applied. Okay, sir. So hence x minus epsilon to x plus epsilon. This is a subset of AB. Okay. So for any x inside AB, we can find an open interval centered at x, which is a subset of AB. Okay. So that means this AB is an open set. Okay. AB open set if for every x we get an interval of this type, which is a subset of that set. Okay. So since x is arbitrary, so this AB is open. AB is open. Okay. It's an open set. So every open interval is an open set. Okay. Right. But you will see the other way it is not. Every open interval is an open set, but every open set may not be an open interval. Okay. We will see that. Clear. So is it clear? Okay. So we will write another equivalent definition of this open set. Equivalent definition of open set. So we can describe open set using this interval concept also. Okay. So another equivalent definition is this. Okay, so we have seen whenever there is an interval, we can always get an interval of this type, x minus epsilon to x plus epsilon. Okay. So we can describe open sets using intervals only. Okay. So equivalent or another definition of open, say to be open if for each x inside G there exists an open interval I such that x belongs to I and it is the subset of G. Okay, that means for every element inside G there is an open interval which contains x. Okay, and is also a subset of the original set. Okay, so instead of looking for an interval of this type, it is sufficient to find any interval, any open interval which contains x and is inside G. Okay, great. So this can also be taken as the definition of open set. Okay. For every element inside this set, there exists an open interval which lies inside the set and contains the point x. Okay, and for take any arbitrary point, you should get an open interval around that point, which is also inside the whole set. Okay, right. So that way you can show. This is another alternate definition of open set. Okay. So under what condition a set is not open? Not open will show me. Under what condition a set is not open? Open if for every x there is an open interval. Okay. So what is the negation? Negation flip the G is open means for every x in G there exists something. Okay. So what is the negation? G is not open. Not open will G is not open means, so opposite of this negation of there exists, it will be negation of for every, it will be there exist. Okay. So every element has an open interval containing it. Okay. The negation will be there is an element for which there is no such open interval. Okay. So for every x there exists an open interval. There exists open interval. Okay. The negation will be there exists an x inside G for which there is no such open interval. Okay. For which there is no such open interval. There is no open interval. I satisfying x belongs to I subset of G. Okay. If this happens, then we can say that the set is not open. Okay. Means if you can find at least one point around which there is no open interval, okay, then we can say that it's not an open set. Okay? Huh? Oh, acha. So if you can find one point around which you cannot construct any open interval which lies in the set G, okay, then we can say it's not open. So can you say, what can you say about this? What can you say about this set, say 0 1. Okay, say closed interval 0 1. Okay, is it an open set or not? Huh? Open or not? Open or not? Huh? Not open. Why?
So because 0 and 1 both have one side of the interval.
So if we take any interval containing this 0, it will contain some points which are less than 0. Okay. So if we write something like x minus epsilon to x plus epsilon, any open interval containing 0, okay, will always contain some points which are outside the set. Okay. Here also, any open interval containing 1 will have some points which are greater than 1. Okay. So that's why it's not an open set. So we'll just justify this. Okay. So let us see. So this is exercise. Is closed interval 0 1 an open set? Okay. Open. So your solution is no. It's no. 0 1 is not open. Is not open. Right. 0 1 is not open as any open interval as 0 belongs to this. Okay. 0 is an element of this set, and any open interval 0 minus epsilon to 0 plus epsilon, okay, will contain points outside. Means that interval will not be a subset of 0. Okay, will contain points outside 0 1. Okay, outside 0 1 will contain points less than 0. Okay, less than 0. So this will not be a subset. Minus epsilon to epsilon is not a subset of 0 1. Okay, it will contain some negative points. Okay, so it is enough to justify for 0. Okay, we don't have to justify for 1. It is enough to find at least one point. Okay, just one point which doesn't satisfy this. Okay, so this is not an open set. If it is something like this, then also it's not open, is it? Right half open interval 0 1. This is also not an open set. Okay. But 0 1 is an open set. If it is open interval, already we have shown every open interval is an open set. Okay. So if your question is show that 0 1 is an open set, okay, how you show? We have already seen. So you just take epsilon as minimum of x minus 0, 1 minus x. Okay, take epsilon as this, and then just show. Okay, just like we have shown. Right. So this is an open interval. Okay. Or if you use the alternate definition, it's obvious. Okay. So now let us see another one. Check whether this is an open set. Check if the set of natural numbers, okay, n is an open set. Open set. The set of natural numbers, is it open set? The set of natural numbers. The open set will be means for each natural number, can you find an open interval which lies inside natural numbers? Huh? You cannot. You cannot find. Okay, natural numbers. These are the natural numbers. 1, 3, 4, 5, 6. Okay. Say for 2, you can never find an open interval which is a subset of natural number, because every open interval containing 2, it will contain some points which are not rational, not natural numbers. Okay, because you will have points of this type, say 2 point something, 2.1, 2.2 like that. Okay, between any two real numbers there exist infinitely many real numbers, rational, irrational. Okay, so actually the set of natural numbers, it is not an open set. It doesn't contain any interval. Okay, there cannot be any intervals inside the set of natural numbers. Okay, so it is not an open set. Okay, natural numbers are discrete. Okay, there is a lot of gap. Between 1 and 2 there are so many real numbers which are not included in n. Okay, so n cannot be an open set. So we will just justify this by writing the set of natural numbers cannot contain any interval. Okay, because any interval contains at least one rational point, at least one irrational point. So the solution is, so this is actually called the density property of R. So the set of natural numbers is not open. Okay, open as it cannot contain any interval. Okay, it cannot contain any interval. Cannot contain any interval. Any open interval. Open interval. Okay. This cannot contain any open interval. So in particular, say it cannot contain any open interval, as any open interval contains both rational as well as irrational points. Open interval contains both rational and irrational points. Both rational and irrational points. Okay. So those irrational points. So no open interval can be a subset of n. Okay. Hence, no open interval can be a subset of n. Okay. No open interval can be a subset of okay. Open intervals cannot be subsets of n. Okay. So the set n cannot be open. Okay, it's not an open set. Right. Okay, similarly, another exercise, the set Q of rational numbers. Okay, this is also not an open set. Rational numbers. Q of rational numbers is not open. Okay. Show that the set Q of rational numbers is not open. Okay, so the justification is similar. The set of rational numbers cannot contain any interval. Okay, because every interval contains both rational as well as irrational points. Okay, so the set Q is also not open. Okay, this, say, what is this set? Say 1, 2, 3, 4. Okay, is it an open set? Check if this set 1, 2, 3, 4 subset of R is open. Is it an open set? So it contains only the points 1, 2, 3 and 4. Okay, it doesn't contain any interval. So it's not an open set. Okay. So the justification is similar. This set cannot contain any open interval. Okay. So this is not an open set. Okay. Right. So now we have a theorem. If you take the union of two open sets, you will get an open set. Let's see, this is the theorem. Union of two open sets is open. But before that, note that, so whether the empty set is open or not, phi is an open set. The empty set phi is an open set in R. So how do we justify it? It is an open set. Why? So the definition of open set says that for each element inside the set, we should get an interval which contains that element. Okay. So here, what is happening? or not? Here the set phi itself doesn't contain any element. So we cannot test the condition. We cannot test the condition. Okay, the set will be open if for every element in that set we can find an open interval which contains that element. Okay, and is a subset of this. So here the test cannot be done. So what should we conclude? It is open or not? Can I say that it is not open? No? So what was the condition for not open? G is not open if there is an element for which there is no such open interval. Okay. So if I say phi is an open set, phi is not an open set, then I should justify it by finding out an element inside phi for which there is no open interval containing that element. So can I find such an element inside phi? We cannot find because phi doesn't have any elements. Okay. So it's vacuously true. This type of things is vacuously true. So I cannot say that phi is not open. So what is the only other possibility? Either a set is open or it is not open. Okay. So phi is not open. That is clear because we cannot find an element which doesn't satisfy the given condition. Okay. So we have to agree that phi is an open set. Okay. So these are vacuously, this is true. Phi is an open set, it is vacuously true. Okay. So this type of things are written as vacuously true. Because we cannot justify that it is false. Right? Say something like this. So this type of statements appear very much in the mathematical logic. Okay. Say suppose this is a box. And I say that every animal inside this box is a lion. So am I true or false? Every animal inside this box is a lion. So true or false?
You
You can?
We cannot say anything without opening the box.
Achha, I have opened. Now? Okay, so here also this vacuously true things will come. If you want to justify that no, I am false, then what you have to do? You have to open the box and find out an animal which is not a lion. I said that every animal inside this is a lion. So to prove me false, what you will do? You will open the box and try to find out an animal which is not a lion. So can you find that? You cannot find because there are no animals here. So you have to agree that I am true. I am correct. Okay, so that's the thing of this bivalent logic gives you some vacuously true statement. Okay, even though it's meaningless to say this, but we cannot say that it is false. Okay, false होते गले you have to find an animal which is not a lion. Okay, but we cannot do that. We have to agree. ठीक है सर बाबा. Debate is good. To avoid that debate, we have to agree that okay, everything is lion. That is why these are called vacuously true. Okay. So this phi is an open set. This is also vacuously true. Okay. So what is the meaning? Meaning is that to say that phi is not open. Okay. If I want to say that phi is not open, we have to find an element in phi, okay. an element x in phi for which there is no interval containing x and contained in phi, okay. And contained in what? If I want to say that phi is not open, I have to find an element x in phi for which there is no interval containing x and contained in phi. Okay. But this is not possible. This is not possible as phi is an empty set. So I cannot find such an element. But this is not possible. Possible as phi is empty. As phi is empty. Okay, so we have to agree that phi is an open set. Okay. And another thing is R is an open set. So that is not recursively true. That is always true. R itself is an open set. R is an open set. So how do you justify it? It's very simple. That X belongs to R, the set of real numbers. Okay, be any element, be any point. Any point. Okay. So take any interval, then any interval, say x minus 1 to x plus 1. Okay. This is always a subset of R. Okay. Because R is the universal set here. Okay. So whatever interval you take, by definition it is a subset of R. Okay. So then any interval, say this is a subset of R. Okay. This is a subset of R. So therefore satisfies. Okay. Then any interval, say x minus 1 to x plus 1 satisfies x minus 1 x plus 1 is a subset of R. Okay. So therefore R is an open set. R is open set. So this has proof. The set of real numbers is open. So next is I have to show that if I have two open sets, then their union is open. Or say let us start with intersection. Or yeah, so let us start with union. Union of two open sets is open. Union of two open sets. Open. So how you prove it? Proof is very simple. Let the G and H be two open sets. Okay. Be two open sets. Okay. Then I have to show G union H is true. Okay. So if G union H is phi, it may happen that their union is empty. Okay. Then already we have seen that phi is an open set, and then G union H is open. So if you start with two open sets which are empty, then obviously their union is phi which is open. Okay. So let G union H is non-empty. Okay. Let this be non-empty set. Okay. And let X belongs to G union H be any element. Okay. Be any point. Okay. Right. So what I have to show? I have to find an open interval containing X and which is a subset of G union H. Okay, that is what we have to do. Okay, so how will you do this? Let X belongs to G union H be any element. Then, so if X is in G union H, then this will imply what? X is either in G or X is in H. Okay, so X is there in one of the sets. So suppose X is in G. Okay. Then suppose that X is in G. Then what happens? G is already open. It is given that G is open. Then since G is open, so there exists an open interval I such that X belongs to I and it is the subset of G. And there should exist an open interval containing X, okay, which is a subset of G. Okay. Therefore, X belongs to I is a subset of G, and again G I can write it is a subset of G union H. G is always a subset of G union H. Okay. So this is always there. G is a subset of G union H. G is always a subset of G union H. So ultimately I can write that is X belongs to this interval I which is a subset of G union H. So given any element inside G union H, we can find an open interval which contains X and is contained in G union H. Okay. So this we have obtained by supposing that X is in G. So we can also suppose that X is in H, okay, and then apply the same thing. Okay. So similarly, similar is the case. Similar is the case is if X belongs to H. Okay. Thus, G union H is open. Okay. So if I take the union of two open sets, it is an open set. Okay. Union of two open sets is open. Okay. So we will see that not only two, actually many. If you take many open sets, thousands of open sets, then also their union is open. Okay. So that is the next result. Next result is arbitrary union of open sets is open. Arbitrary union of open sets is open. Right. Arbitrary. Yeah. Arbitrary means you take any number of open sets. Thousands, lakhs, more than that. Okay. Any number of open sets. Then you take the union, it is always open. So how will you write this thing? So there is a system to write this. Okay. We denote it this way. Okay. So suppose you have three open sets. So usually how we denote? G1, G2, G3. If you have say 100 open sets, so G1, G2, G3 up to G100. Okay. If you have much more than that, then say something like G1 billion. Okay. Can there be much more sets? Arrow set factor currently. There can be many more sets. Okay. So it may happen that suppose think about this. Suppose I write open sets as this A, B, C, D. If I use these letters as open sets, then how many open sets can I write at most? Z 26. So with just letters, I can write only 26 open sets or symbols. I can just use 26 symbols. But after that, if I use this numbers index, okay, A1, A2, A3. So with indices, how many we can write? Infinitely many. 1, 2, 3, 4, 5. What will happen if this 1, 2, 3 also gets exhausted? They exhaust to even with what? This may get exhausted. Okay. In your first unit, you have seen countable, uncountable sets. So it may happen that your so this is just countable. Na? This is a countable collection. If I write the indices as natural numbers, it is just a countable collection, very small collection. But in your earlier unit, you have seen there are uncountable sets also. Okay. What is called 0, 1, 0, 1 is uncountable. Or maybe I could not do it in class. I have given a video, you see. The open interval 0, 1 is an uncountable set. Okay. So there are much more elements than this 1, 2, 3, 4, 5, 6 natural numbers. Okay. So something like this. If you take a collection of say open intervals of this type, a comma infinity, where a is inside the set 0, 1. Okay. So this itself is an uncountable collection. Okay. You cannot write it with this natural number index. Okay. So it will contain sets of the type say 1 to infinity. It will contain 1.1 to infinity. Okay. It will contain 1.11 to infinity. Okay. Many others. So actually there are uncountably many indices here. Okay. So that is what I am saying. So if I write the sets this way, then I can denote this collection as what? The set of AI such that I belongs to the set of natural numbers. Okay. So this set N will be called the index set. Okay. And this one, if I write this collection, I will write this as equal to the set of A infinity such that A belongs to real numbers. Okay. So here the index set is the set of real numbers. Okay. So this is an uncountable collection. This is a countable collection. Okay. So there are much more members in this family, okay, than this family. Here. So that is why you have to write something like index. Let Gi such that I belongs to capital I. Okay. Be a collection of open sets. Be any collection of open sets. Okay. collection of open sets. Okay. What is the time? Time you see? Huh? 15 minutes left or what?